Hello, and welcome to Part B of Chapter 7 for Finlandia University's Earth History class. We continue our conversation on earthquakes today, and then maybe, depending on time allotment, move into volcanoes for a little bit. I want to say before we get going here that I am a bit sick, so if I sound nasally and weird in a certain way, I might take a break to blow my nose or something. Is what it is, right? Sickness happens. So let's get into it. We've been talking in this class so far about earthquakes, what they are, how they work. I ended a bit with seismograms last time. A seismogram basically is a more or less straight measurement of the up and down motion of the earth. The earthquakes, as a real quick reminder, come in the form of P waves and S waves through the body and Love and Rayleigh waves through the surface, depending on your classic physics of the direction of the energy versus the direction of the motion of the particles. Right? The seismograms, these are super mechanical versions of them naturally. Modern seismograms aren't weights on strings, but modern seismograms work along that same basic feature. The seismograms shown here produce seismographs. These are literally the shaking of the ground below the seismogram, and they correspond with the arrival of P waves, S waves, and surface waves as shown here. P waves are primary waves, so the fastest to go through the ground. They arrive first. And then as they start to peter out, the S waves hit. That's your first major spike. And then as those start to peter out, eventually the surface waves come, and those shake the seismograph the most because naturally they're on the surface. This actual seismogram readings are much more complicated than this very basic introduction. There's P1s and P2s. There's a whole bunch of different ways to read and interpret seismograms. But for sake of our conversation, we can just keep it nice and simple and discuss the first wave that hits is the P wave, then the second blip is the S wave, or what have you. So how is this stuff useful? How is knowing how the earth shook and the different types of waves beneficial to us? Well, first and foremost, it allows us to calculate where the earthquake actually happened. This can be very useful for many things. The earthquake happened underwater. You might have tsunamis showing up. If the earthquake happened on land, I might be able to tell you where the majority of the damage was dealt. The earthquake may have happened very near to a town, and the town is wrecked essentially by this earthquake, but you wouldn't know that unless the town told you. This stuff is useful for that matter. Also, calculate other various things such as stress on faults or what have you. Anyways, to calculate the location of an earthquake, we take into account the fact that P waves and S waves travel at different speeds. Your P wave always shows up first, your S wave always shows up second, again, given the way the energy propagates to the medium, in this case, the Earth. Using this information, we can calculate the distance they're covered and create what are called time travel curves. So if we find 3 of these time travel curves shown here on the left, we take 3 of these time travel curves, we create what are called great circles, or essentially how far away from the location of the seismogram, say here, Kingston, Jamaica, Toronto, Ontario, Regina, South Saskatchewan, how far away from the earthquake was a seismogram. And then we can also use that information to dictate, okay, I know that my P wave here showed up at about 4 or so minutes after the earthquake happened. All right, and that is for Saskatchewan here. So how far away can I get for something to show up in 4 minutes? Cool. What is the maximum distance at which something happens and it hits my seismogram in 4 minutes? This circle, this green circle here, represents how far away an earthquake would have to be for Saskatchewan for the pulse of that earthquake to arrive in this amount of time, this first primary wave. Toronto also felt this earthquake, but they felt it at 6 minutes. So, what is the area of a Toronto seismogram that you can feel 6-minute pulse from, a 6-minute primary wave? And again, here, Kingston with a, what's that? 7.5 minute, right around there. These three different locations, all these circles, all indicate any place at this circle, on the circle itself, any place on the circle could have been the location of the earthquake. And then what happens is you plot all three of these great circles together on a map, and what you find out is all three of these circles will all land at one location. This location is the only spot where the waves will travel and arrive at these different seismogram locations, all exactly matching the curve that we have here. So this curve here, this primary curve, shows you exactly where the location of the earthquake was relative to the various seismograms that we use. And the arc of this curve and the secondary S-wave curve also tells seismographers, people that study earthquakes, what have you, various interesting facts about the earthquake. Again, this is an introductory class. I'm not going to go super deep into it. If this stuff is of interest to you, leave a comment down below. I can forward you towards good sources of information on seismology, and this is a huge, cool, interesting can of worms. Excuse me. Hate being sick. So, that's cool. And something else you can notice here for this particular example is maybe fictional. I'm unaware. Is it safe if it's fictional? I'm going to assume this is fictional. Where is it? Where is the earthquake located? Out here by the border of California. Well, that leads us into this conversation. Most earthquakes, where do they occur? Earthquakes tend to occur at plate boundary zones, meaning, as we've talked about in previous classes, the Earth essentially is a bunch of floating plates on the asthenosphere, right? I used the analogy of macaroni rolling around in boiling water. That's a poor analogy, but it's the one I chose when I started teaching this class. As these plates move and jostle around for position, they're going to bump into each other. They're going to scrape by each other. They're going to release energy in this process of moving, right? Move your hands back and forth a lot. What's going to happen? Your hands heat up. That's energy caused by the friction of your hands. To a certain extent, that's kind of what goes on here. It's not necessarily 100% accurate, but the analogy holds nonetheless. Most commonly, we find earthquakes at transform boundaries. These are the strike-slip faults. These are the faults that occur where the motion is lateral plate to plate, as opposed to subduction zones where one plate goes under another, or divergence zones where they separate apart, something like that, right? We've talked about transform boundaries before. The fault motion is vertical, the plate motion along that line of the fault happens. So this allows for earthquakes. You have two plates that are stuck next to each other, but they're moving in such a way that eventually you get a snap of that motion. Again, imagine gluing the sides of your pointer fingers together and slowly pulling one hand down, one hand up. Eventually, you're going to break that glue, and that break, more or less, is an earthquake. Not every time a plate moves, you have an earthquake, though. That's pretty obvious, right? We have something called fault creep, the small, slow movements along faults that occur without violent earthquakes. If you want to get super technical about it, earthquakes happen literally all the time. But earthquakes usually release at such low energy, ones, twos, what have you, that you don't notice them. You have tens of thousands, hundreds of thousands of earthquakes going on all the time as these plates are slowly grinding and moving and jostling with each other. This map here shows all the earthquakes since 1898. You'll notice that's a lot of earthquakes. But if I asked you to think of some earthquakes, you could probably think of, I don't know, 8, 10 earthquakes off the top of your head, maybe, right? This is because the earthquakes that matter to us as humans are the ones that cause extreme amounts of damage. We talked about that in the last video. The different scales of earthquakes. Where are we at? Oh, someplace around here, I thought. Maybe it wasn't. I know we talked about that. There we go. I passed right by it, right? Mercalli scale measures the damage done by an earthquake. That's the thing we actually care about. If the earthquake doesn't do anything, doesn't affect us, we tend not to bother because they happen very short in a very short amount of time. And okay, congratulations, earthquake. Big earthquakes ever cause damage. So the bright spots of green on this map here, notice very much along the Pacific Ocean, the Ring of Fire, right? These earthquake zones are the ones we care about. You can have earthquakes in other locations, such as divergent boundaries or spreading centers, due to, again, the fact of the spreading, right? Just picture what's going on here, and an earthquake is any breaking of rock and releasing of energy. You can have earthquakes mostly everywhere, even plate interiors, as we'll get to, but it is important to remember that the majority of the large earthquakes, again, let's look at this image, the majority of the large earthquakes are along these transform plate boundaries. Plate interior earthquake here, such as the New Madrid earthquake, and I believe that's Missouri in 1811. Why do you have a plate interior earthquake? Well, something is causing the interior of that plate to undergo some sort of deformation of motion, thereby causing breakage of the underlying bedrock, release of energy, and damage. I talked a bit in the last chapter about the actual practical results of earthquakes. Here's a good image of that. That right there, that in the center of this picture, that is the fault line. That's where the rock actually broke. And this planted material here shifted over as a result of an earthquake, a dramatic shift. That's what, a foot, right? About half a meter or so, maybe 3/10 of a meter movement of the actual land. And all this land, this picture could extend to both sides. You can see this is a large swath of land being abruptly moved over as a result of an earthquake. We do have convergent plate boundaries. Again, as I said, all these locations can give earthquakes. The most common at transform boundaries, but divergent, convergent, and of course, non-plate boundary related earthquakes happen too. Convergent plate boundary, what is that, right? Let's go back to our plate tectonics conversations. A convergent plate boundary is when one plate hits another plate, usually one subducts under, right? What's going to happen to that subduction? Well, you're going to get some rock touching rock. You're going to get some bending, some brittle breakage. You're going to get earthquakes, right? Here we could talk about the Benioff zone, or the friction along the downward plunging contact zone. Essentially, that is the top of the downward plunging plate, right? I always like to use analogies to represent this stuff. Put your hands like they're going to run into each other. Put one hand below the other hand. What do you feel as you put one hand below the other hand? You feel some heat, some friction from the bottom of your fingers touching the top of your bottom of your fingers of your upward hand touching the top of your fingers of your lower hand. Maybe if you got finger hair, it's being pulled back. That heat is analogous to the deformation and the friction that happens that causes the earthquakes. The India-Pakistani border had an earthquake in 2005. I believe this one was a pretty big one, actually. That was a result of a convergent plate boundary, this buckling and release of pressure. Right? Shown here. These earthquakes can be rather shallow. They can also be rather deep. The deeper the earthquake is, the more the energy is soaked up as it travels up, less it really affects us. Shallow it is, tend to have more damage being done, right? You have an earthquake go here, maybe you have tsunami, water flow happen, causing major damage. Earthquakes happen when you have rocks moving on the rocks in a violent enough fashion that they snap. That's the easy way to describe an earthquake. If you have plates moving, not playing well with each other, you get this stuff happen. Usually the vast majority of the time, the like 99% of the time, it's not a big deal. The rocks break, the rocks snap, they creep along slowly. You don't actually get any noticeable impact or damage to the rest of humanity, the rest of the world. However, sometimes they do have that issue. you do get that break, you do get that explosive release of energy, the massive devastation that's caused by, again, an earthquake. So, quick recap. What are the mechanisms at the three types of tectonic plate boundaries? Well, again, the mechanisms all evolve in the same idea of the rocks at the plate boundary having an issue where they're moving. They don't want to move, but they are moving. And eventually, if the movement is strong enough and persistent enough, you can have a breakage of the connecting material, snapping of the glue between your fingers, right? Causing a quite powerful or quite minor earthquake. The Benioff zone is this picture, those yellow stars, right? Why do only shallow earthquakes occur at the Mid-Atlantic Ridge? Well, that is an interesting question. If you notice here, here's the Mid-Atlantic Ridge, not a lot of bright green dots, right? You don't hear a lot about earthquakes happening in the Atlantic Ocean. You don't hear about tsunamis happening in the Atlantic Ocean. The Indonesian tsunami over here that, caused massive destruction, loss of life around the 2010s. Look at how bright green these dots are, right? You don't have that over here. This is a divergent boundary. Picture divergent boundary. Why do you think you don't have the same massive amount of breakage of plate material at a divergent boundary you do at a convergent or strike slip boundary? That should provide you with an answer. Earthquake damage and hazard mitigation. Earthquakes are interesting. Earthquakes are cool. How they relate to us? Well, mostly earthquakes are, for the sake of this class, seismology is researched as a way that earthquakes are going to happen. We can't do anything about it, but we can help reduce the damage that's caused by them. So, what can we do about earthquakes? Well, we can look at the rock and soil involved, namely the bedrock, soil type, liquefaction, soil water content, and water table. All of these components of the bedrock and underlying soil play a big part in mitigating the energy that's being transferred through. Because, right, let's remember, what is an earthquake? That is a energy pulsing through the ground. And P waves and S waves, usually then Rayleigh and Love waves for the surface. But the way those P waves and S waves push through the ground play a big factor in what happens to the ground. If the rock reacts very strongly, feels all the force of that earthquake, it's going to shake a lot more than if it doesn't feel the result of that earthquake. We could take these ideas of material being resistant to or flowing with the shaking of the earthquake, and we can design structures for earthquake-prone parts of the world that reduce the negative effects of said earthquake. What do I mean by this? Well, remember, one of the ways to scale earthquakes is energy, but another way that's probably more beneficial to us as society is the damage they're caused, right? Damage they're caused. And we will notice that you can have earthquakes in, say, modern-day California, large, powerful earthquakes in America that don't cause a lot of damage, and you could have smaller earthquakes in less developed countries throughout the world that cause massive amounts of damage. That's because you have the money, you can think about construction of the material, and then you can design, say, houses, highways, bridges, what have you, that can work with the earthquake and essentially mitigate some of the energy release. We do have a lab covering this subject. I suggest when you go through the lab, you will kind of see what I'm talking about here. I can talk about this stuff, but seeing it with your own eyes, these effects, I think is very informative. Likewise, if this is something that you want to learn more about, comment down below. Look up earthquake building construction. You can find lots of very interesting images of people designing buildings and bridges, what have you, that respond well to earthquakes and don't collapse. Real cool stuff. There's a Sumatra earthquake in 2004, and of course the Tohoku earthquake in Japan 2011. Those two earthquakes, very different in result of loss of life and loss of property, because One of those countries is less developed. One of those countries is more developed. One of them could afford to worry about earthquakes. The other one kind of can't. So let's take a look at this example here. We have an earthquake right here near the epicenter, right? As close as you get to the earthquake, that dictates how powerful the earthquake's going to be, right? Closer to the source of the energy, closer to the grenade going off, the more likely your hand's going to get blown off. This black color here represents most powerful, most highest tsunami waves, what have you. Notice how it peters off pretty dang fast, right? You get 8-10 foot waves right near the surface here, but you go out not very far away from Japan itself, and you're getting little middling half-foot waves out here in the yellow, right, and the green. That's pointless. That's a beach. Sure, that's not very damaging. But that being said, that has to do with the amount of energy coming off and the true danger involved. So Tokyo, Japan, on the Ring of Fire, right? Let's go back to that image. Tokyo, Japan, on the Ring of Fire. Look at that. You can't even see the country. Actually, no, it's Korea. There's Japan. There we go. On the Ring of Fire, very potent, needs to deal with this stuff on a regular basis. How are you going to construct your buildings when you have 10-foot tall tsunami waves very likely to happen and hit your shore? Well, let's talk about that, right? Here we have a cartoon of the 2011 Tohoku earthquakes in Japan. Notice right here you have a breakage of the material causing the earthquake to rupture, starting, as said here, about 32 kilometers below the surface, right here, and it propagates west, meaning the energy goes through this strong crystalline bedrock here, causing ground shaking in the Miyagi Prefecture. Look at it all shaking, right? This fault rupture switches directions and propagates eastward and upwards violently, punching upwards both the soft sediment near the seafloor and the underlying deep water. So initially, the rock pushes towards the west here, shaking the bedrock, but then it, every action is an equal opposite reaction. It punches east, hitting this soft ocean sediment right here. Energy dissipates through that. This ground rock here isn't going to move, isn't going to contort or deform to this energy release. It's just going to kind of set it through. But the sediment is going to buckle, is going to respond in kind. It's going to push up as shown here, and then the water is going to again respond in kind and be shoved up as well. So instead of just having an earthquake through the rock, now we have big old wave, right? Resulting large bulge of water spreads out, moving to the sea and towards the shore. Deep ocean, in the deep water of the open ocean, the tsunami travels rapidly as a series of relatively small waves decked by offshore buoys. This ain't a big deal as it heads out of the ocean, right? Again, as shown by this map. Once the earthquake hits, the size of the earthquake drops dramatically. Red, that's a foot and a half. That's kind of pointless, right? 6, 7, 8, now we're talking dangerous waters. Even 4, you could argue, I don't want to get hit by a 4-foot wave, right? This is really only danger spots. So close to the earthquake. And cool enough, we can watch as this earthquake leaves, and we can direct, again, as said by here, we know it's the large bulge of water and its direction it travels. This tells us maybe the direction of the earthquake and how it broke, right? I can draw almost a direct line right back to the epicenter here. That's where the vast majority of the energy dissipated out in this linear direction here. Didn't dissipate out these ways, did it? As shown, evidenced by the tsunami height. A lot of cool information in these diagrams, right? A lot of stuff you can think more in depth about. And of course, oh no, look at the buildings falling over, this poor ship, right? Tsunami rushes on shore, causing death and destruction. Again, look at the waves. If the vast majority of the energy is traveling more or less linear in this path here, where things happen this way, exact same thing, right? Just now you're hitting the shore. The Fukushima nuclear reactor gets smashed by gigantic tsunami waves. And it is worth noting, again, when you do your labs, you're going to kind of get a better understanding of this. This is bad. This ain't fun, right? But the Fukushima nuclear reactor didn't collapse from the earthquake. It got beat up by the tsunami. Again, your labs are going to elucidate this a lot better. And this is a visual component of earthquakes. So I can try to explain stuff, but even that simple, the first question or so of your lab with the plastic cup and the penny and shaking and what have you will teach you a lot about the way things respond to earthquakes. So can we predict earthquakes? Well, the long term, yeah, you could say well, earthquakes are likely to occur, right? That is this image. Earthquakes are likely to occur where earthquakes are likely to occur. We know that they tend to occur during transformed plate boundaries. They also can occur at divergent, plate interiors convergent, in particular the Benioff zone, but transform is what we need to look at. In the short term, it's more of a monitoring than a predicting conversation. You can look for, it says here, foreshocks being before the earthquake, and say, oh, something big's coming, I've got a little foreshock. You can monitor for plate motion, but the way earthquakes work, you can't see the rock and measure, how much it's deformed and graph that on a brittleness chart to say, okay, if in another 18 minutes it's going to break. We don't have the capability. So a thing we can do really is say the likely to occur here. Ooh, I see a foreshock. Tell people, and hopefully that provides them with enough time. And again, the majority of the damage, you see a lot of damage more so from tsunamis than from earthquakes if you build your structures to care about earthquakes. So, yeah, this map here shows peak acceleration expressed as a fraction of the standard of gravity. Essentially, how scary it is to have an earthquake. Studying the Earth's interior. Cool. So we talked a bit about earthquakes and the way and what that means for seismologists. That being said, earthquakes aren't the only thing they study. We can also, as said here, discuss the interior of the Earth. What's below the ground that we don't have to dig into it and see. It's the benefit of science. I need to visually see something with my eyes to understand what's going on. In a homogeneous media, i.e. something that's consistently that one thing, a piece of basalt, sand, something like that, waves propagate equally in all directions. Meaning, if you jump and then land and smash your feet against the ground, the energy is going to ripple out through the floor equidistantly in like a big circle, right? Like drop a stone in a puddle of water. That's exactly what we're talking about here. The velocity of that energy depends on the nature of the material waves are traveling through. You may know, the speed of sound is 670 miles per hour, something like that, right? Sound travels faster through water. Energy travels through different mediums at different speeds. The speed of light in a vacuum is 3 × 8 meters per second, but the speed of light in, let's say, air is slower than that because a vacuum in space, for example, is different than the air that we have outside our window. Light actually travels slower through the air. And lastly, waves, we gotta get into physics here a little bit, but waves can refract and bend off of objects while moving from one to another. This is Snell's laws, things along those lines. Essentially, we know how waves react to differences in density and to differences in type of matter, solid, liquid, gas. And we can use this information to study the waves in the Earth and learn about, as I said, those waves. In 1909, that name there, not going to try to pronounce that, discovered what we now call the MOHO, because who wants to pronounce that name, right? A crust mantle boundary layer that refracts, or waves arrived at distant earthquakes faster than closer ones, refracts waves that reach it. Got a picture here. This was developed because you would expect waves to sort of appear in this equidistant fashion if the Earth was just one solid chunk of material. But what we came to find out when we studied seismographs, and we studied these guys here, what we noticed when we look at multiple earthquakes is that if you, again, model the Earth as its shape, and you think about how the earthquake waves would travel through material, we notice that these top earthquakes and these bottom earthquakes, the arrival times of, say, the P waves, S waves, what have you, alter depending on distance, and did not alter necessarily based solely on a uniform amount of distance. Namely, this blue wave here, this direct wave in this top layer, this lithosphere layer, if you will. Actually, no, not lithosphere. We'll call that crust. This top crust layer, the blue wave hits the 100 and the 400 kilometer seismograph stations, kind of how we would expect it to. Meaning the 100-kilometer away earthquake station received the first wave, and then 4 times the time later, the 400-kilometer away station received the wave, right? So you can exactly track that. However, what is interesting is down here in the upper mantle, the waves that essentially went more vertically down refracted up, and they traveled faster through the mantle. Hence here, these waves of energy are further away, traveled through the mantle, and then actually would arrive at the 400-kilometer station before the direct waves would. This blue wave kind of follows a very nice to follow curve if you plot it, but the red wave doesn't. The red wave jumped ahead because it was able to get down into a medium down here, right? The mantle, where it could travel faster. Essentially, it switched lanes over from the carpool lane going 55 to the passing lane going 70, and it skipped around. That's cool, right? I'm pretty sure we've never dug deep enough to find the MOHO, find this discontinuity between the crust and the mantle. We don't know what it physically looks like, but we know a heck of a lot about it because we can see the difference in the speed that these waves undergo, and then we can back calculate and find analogous materials to these speeds that we calculate, and we know, oh, hey, the upper mantle is made of this particular material, and it's at this particular consistency. Again, that's something that moving visuals do a lot better job of. I'm trying to run through this subject very quickly. People spend their life studying the MOHO, right? Comment down below if you want more information. I can direct you towards something that hopefully would be of more importance to you. Right? Using this information, we can determine, for example, the structure of the mantle, how big it is, where this discontinuity is that we're talking about, given different locations of earthquakes and seismic events, and different seismograph stations throughout the world. We can also, again, this provides us insight into the discovery of the core, why we say we have a solid iron inner core and a metallic liquid outer core, right? Things along those lines. Shadow zones appear, right? It's all really cool. This map, I think, does a pretty decent job of this conversation, in particular referencing the core exclusively. Namely, if the core was just, if the Earth was just solid one material, these waves would all be equidistant exclusively, right? But what we find is when an earthquake happens here, only a certain amount away of stations receives their P and S waves, these primary and secondary waves, in a linear fashion, more or less, it's for sake of conversation, in a linear fashion. But the waves that would propagate into the core run into some issues. Namely, the outer core is liquid, such liquid that the S waves don't actually propagate through that. What do I mean by that? Why would S waves propagate through liquid? Well, let's go back. Let's discuss these two different types of waves, right? P waves and S waves. The P wave is your pushing wave, right? Taking the slinky, pull it back, let it go. This would be analogous to, say, blowing air at someone. That sort of would be a P wave. A sound wave would be a P wave, right? An S wave, that is where you take a slinky, you pull it off to the side. All right. So that would be analogous to, you have your hand under, well, actually, I'll go back with the air analogy. That'd be analogous to moving your hand, waving your hand in front of something. Okay? So which do you think you're going to hear? Which do you think you're going to feel over distance? Me talking to you, P wave fashion, or me waving my hand like an idiot, trying to push the air all the way towards you, right? I'm not going to move the air doing that method. The S wave isn't going to travel through a fluid medium simply by the fact of its shear wave capability. Liquids don't shear. So, again, a lot more detail if you want, comments down below, what have you. What this means is, since we don't have S waves going through, we don't have S waves where we would expect to have them in the shadow zones, or actually the entirety of the bottom of the Earth here, we don't have these S waves. That means that they're being stopped by something that is fluid, something that is liquid. Hence why we think there's a liquid outer core. And furthermore, we can study the way the P waves work. We get this ridiculousness of P wave travel times with reflections, refractions, what have you. This brings forth the idea that there's this solid inner piece that's reflecting and refracting through the liquid core that is like, again, reflecting and refracting the waves in certain ways to create this, as shown here, ridiculous looking shape of the P wave reflections. And the interesting part about all this is all this information came from people studying these. People studying these seismograms throughout the world and correlating their locations with their times, with their distances from earthquakes, and noticing, we have these staggerings of P waves and S waves. And surface waves, they barely go anywhere. Like, the epicenter here is your surface waves are going to stop at about the distance of the word epicenter. None of this is going to have surface waves, but it will all have P waves and S waves. I don't know. I think that's fascinating. Hopefully you do too. This information gives us average densities of materials. The crust having the lowest density, the core having the thickest density, again, going with the materials that they're made out of. And this information has also helped us understand the Earth's magnetic field. We all know the Earth has a magnetic field. You've played with a compass before in your life, I'm sure, right? And since we have this weird liquid fluidity to the Earth, and we have what we perceive to be metallic components within the interior of the Earth, that allows us to say, hey, when I move something around metal, what do I get? I get a magnetic field. Maybe the same, that dynamo action that allows me to create magnetism and electricity, they're kind of similar, right? If you get into physics, the thing that allows me to make magnetism, electricity here on Earth in my generators, is kind of akin to what the Earth's interior looks like. Maybe the Earth's magnetic signature is derived from this relationship that I've discovered via seismology. Geology keeps feeding itself and coming itself back together, right? This convection, this spinning of the mantle and the outer core with respect to the inner core, moving the electric field around, moving the magnetic field around, creating, again, magnetism. And this magnetism is what we talked about previously when we talked about plate tectonics and how we have evidence of shifting magnetic poles, time it takes to accrue these sediments, what have you. It's all cool, it's all ridiculous. It's all very exciting. Cool. That was chapter, whatever chapter, what chapter is this? Chapter 7. That was chapter 7, Earthquakes and Earth Structure. I got a bit more time. I want to dive a bit into chapter 8. Maybe finish it. We'll see how time allots. But let me just quick share chapter 8 with you. There we go. Chapter 8, of course, being volcanoes and plutons. Sweet. So we've been talking a lot about igneous materials, volcanic materials, lavas, magmas, tectonically active zones, what have you. Let's dive a bit deeper into this very important aspect of geology and the Earth in general. Oh, excuse me. So let's start with magma. We've talked already in this class, magma is what we call lava that hasn't busted through the surface yet, right? That's super acceptable definition. What processes, though, form magma, i.e., how do you get it, right? Well, magma is melted rocks. How do you melt a rock? We don't tend to think about rocks as being melted, right? Well, come to find out, rocks melt easily when you do a couple different things to them. Increased pressure being the first one. Duh. You knew that already, right? You got to increase pressure to melt something. Increase temperature to melt something. Funny enough, rocks also can melt with a change in their pressure. If you increase the temperature while decreasing the pressure, the melting point of the rock will go down, allowing the rock to melt at a temperature that's not necessarily what it would be under a higher pressure. And the more water you add to the scenario, the more easily, again, the rock melts. Water is useful here because, right, it's water. So essentially, to go from liquid magma to any particular igneous rock, this looks like a granite we have here, you cool the liquid, increase the pressure, or remove the water. How do you remove the water? Well, if the liquid magma is hot, it boils off. If the water is someplace to go, then you crystallize the magma that you had. I wouldn't say cool, but cool only refers to the temperature component. And what I'm trying to stress here is that temperature, pressure, and water all play a big factor in what type of magma you have, what type of igneous rock you have, and why they exist in the places they exist. Right? This refers, going back to basic physics, kind of physics you talked about in high school. You increase the temperature, increase the energy, increase the water, decrease the pressure, allows the stuff to move around more. Right? Where do we get magma forming? That's how magma forms. It's different components to rock melting. Where do we get this magma formation? Spreading centers would be something we've talked about a lot, right? Your mid-Atlantic ridge scenario. It has asthenosphere oozing into spreading ridges. This is the Horn of Africa, right? Things along those lines. But magma also shows up in the form of a mantle plume. Mantle plumes are hot, big pluminous masses of mantle that are buoyant and float relative to the surroundings. They kind of a big, I'm trying to think of that here. I guess a water balloon, maybe. It's kind of a weird concept to get your head around, right? And then finally, of course, subduction zones. You've seen countless pictures of subduction zones causing oceanic crust to melt, and that melted rock to float up due to differences in pressure. Actually, come to think of it, that mantle plume would probably work well with those images that we've seen, right? Um, Here is the mid-oceanic ridge, mid-Atlantic ridge if you want, or the Horn of Africa Displaying Center. The asthenosphere is coming up here. This rock has been melted by, this rock is melted as it rises. As it comes up here, it loses its water, and it reduces its pressure, and it reduces pressure and reduces its temperature, and it crystallizes, solidifies, creating the igneous basaltic ocean floors that we have. Seen this image countless times already, right? Here's your rising mantle plume. This is your hotspot example here, like Hawaii. And kind of looks like the same thing, right? Just instead of a big crack in the ocean floor, we have a couple of dots where the asthenosphere happens to be bubbling up this way. This is a lot of force here, right? The plates kind of just have to move out of their way. If you have a situation where you have the corner of a plate, like the edge of a plate, the plate can then shift. You can have the divergent zone. If you're in the center of a plate like this, the plate may not buckle, but the magma can work its way through, creating these volcanic hotspots in the Hawaiian Islands. And of course, this image we've seen countless times, the convergent plate boundary, wherein the oceanic crust comes out here, incredible amounts of temperature melt the material, and then the melted material rises up due to differences in pressure, a lot less pressure on the surface of the planet than there is the bottom of the planet, right? And then the increased pressure comes up here, and it spits out volcanoes. Cool. Notice here, it's highlighted something called a pluton. We'll get into that a little bit, but a pluton is essentially these little plumes of magma that never spit out the surface. That would be a pluton. I don't want to go too deep ahead of it. Just a second here. So yeah, those basic processes. We keep seeing these processes in the images we've seen throughout this class, but now we're going to focus a bit more on those individual aspects. About 75% of the Earth's active volcanoes lie within the Ring of Fire. That is the trace of the Pacific Ocean. Chain of subduction zones that subduction zones that convergent plate boundaries. Yeah, okay, well, I already said that. I'm not going to have to repeat this down here. But yeah, we know that already, right? A lot of volcanoes exist there. Volcanoes are very popular at plate boundaries, but again, we're going to diverge a bit more from earthquakes than we did from earthquakes. There's a lot of volcanoes not on boundary zones, right? And also, I think maybe this is defining earthquake a bit differently too, because like this entire ridge is comprised of earthquakes, but it's not all dots. So we'll get into that though. I guess I should know before I go forward. Look how fast some of these plates are moving. Sweet Lord, the Nazca plate, the Pacific plate are just diverging so fast right here. It's nuts. 17 is that centimeters per year, I imagine? It's crazy fast. Crazy fast. So we talked about igneous rocks way back in chapter 3, I want to say, at the beginning of the semester. And igneous rocks, of course, are the crystallized magmas and lavas, right? The most common of these we're talking about here, basalts, granites, and andesites. Basalt is a partially melted asthenosphere. The granite has a lower melting point, and the andesite is well between the basalt and the granite. We talked about these as in terms of felsic and mafic, the chemical makeup of the rock as the deciding factor. But funny enough, these rocks also play a big role in where they're found. Granites are usually continental. Basalts are usually oceanic. So, where do we get continents from? That's a pretty good question, right? Have continents always been around? We have the cycling going on throughout the and all these different parts, right? All these active zones, all these tectonics. Why do these plates exist? Why does they plate on all these things? Why do we have continents? Well, some of the oldest rocks on the Earth are 3.96 billion-year-old Acastinices. Remember, the Earth is what, 6.5, 7 billion years old, we estimate. A 4 billion-year-old rock means that rock has not been melted in that entire amount of time. I think these are found in Australia, I want to say, and maybe a bit in Canada too. But that's pretty impressive, right? This rock was formed some 4 billion years ago, and it's still around. The oldest mineral we find are 4.2 billion-year-old zircon crystals in Australia. Again, we'll get into, we talked about a bit with Bowen's reaction series in chapter 3, but certain minerals melt and minerals deform at different temperatures and pressures. Zircons last a long time. The fact that these zircon crystals are 4.2 billion years old means that they've been able to resist being essentially subducted down deep enough for more than half of the age of the planet. That's cool. Right? I think that's cool. This information indicates that granite-like rocks formed probably about 4 billion years ago. The oldest rocks we have on the planet, about 4 billion years old. There's a good indication that the continents are probably around 4 billion years old. The earliest crust was likely probably mantleite, some kaomatite, meaning the Earth as it existed before what we look at now as Earth was pretty different. We didn't have North America. We know from plate tectonics, North America didn't sit where it sat, but the rock that is North America existed back in Pangea time because we can measure how it moved. But there was a time when the rock that consists of North America did not exist. I'm sorry, I have to go blow my nose. 1 second, please. All right. I believe I'm back. I gotta check, make sure my mic's on. Going back. So, oops. How do these continents form? We know we have a rough estimate about how old they are, but why do they exist? Two active hypotheses that we have today. We don't know for sure, but two thoughts that we have. We could have had some horizontal tectonics, i.e., island arc chains. The Aleutian Islands in Alaska are growing continent, essentially. They're growing continents, and maybe if they grew continents now, they grew continents then. You also could argue maybe there was some vertical mantle plume tectonics, meaning, to go back here, the mantle pushed up some rock. We talked about isostasy, I believe, chapter or two ago. The mantle pushed up some rock, and then when it fell down, the rock stayed there. Super introductory conversation. That this is an interesting topic, though, right? How did the Earth form? These two examples show here. According to one model, early continents formed through a process of tectonic accretion. Top picture there shows a typical island arc showing the position of the trench and the accretion wedge. Note the presence of the Back Arc Basin behind the arc. Back Arc Basin shown here. This is the Aleutian Islands and Alaska, essentially. Maybe those Back Arc Basins originate from the seafloor spreading behind the arc. Cool. Eventually, the seafloor spreading ceases. The Back Arc Basin essentially extends and compresses and connects with something else, causing a collapse of the Back Arc Basin and to the island arc, and the continent is therefore accreted out. So essentially, you had a bunch of volcanic arcs that ran into each other and formed the continent. The issue with, I guess I will say, this is one of those fun science questions, one of those fun geology questions where you can't really test these theories. You can more so find something that seems probable, right? If I told you that North America is formed by a bunch of Hawaiis smashing into each other, you'd probably look at me kind of dumb, right? But America exists, had to be formed somehow, right? This is one plausible reason. And again, but for sake of conversation, instead of having a continental crust here, this would be another island arc, essentially. So, various ways that magmas behave and exist. I will say, however, I'm not super happy with the conversation. I feel as though there's a lot of questions you may have on what I've been trying to discuss in these points, because this is a really complicated subject, right? So again, I'm going to stress, I've stressed it a lot through this video. I'm going to continue stressing it. If you have any questions, want further in-depth analysis, please comment your question. Let me find some resources to guide you to a better understanding of what we're talking about here. So what happens when magmas rise? When the magmas rise, they cool, right? And they solidify. Magmatic composition, funny enough, differs greatly. We talked before about granites and basalts, mafics and felsic rocks. Those not only have different silica contents, which is the felsic mafic comparison, but they also can have different water amounts. Granites tend to have a lot of water, basalts do not. The silica content increases the viscosity, or the essentially how syrupy the water is. The more silica you have, the more viscous it becomes. The more viscous becomes, the less likely it wants to move, right? A very viscous substance is something that does not like to move very much. Gasoline's not viscous. Syrup is viscous, right? And the effects that difference in water has is that it can increase the solidification temperature, if you will, of the magma that has water within it, meaning the dry magma solidifies quicker and hardens faster. So you have all these different components to the magma, and these different components can arise from the source material, can arise from where it's being spit out, many different components. And yeah, they all work together in these fun, intricate manners to produce the variety that we have today. I spoke way back about plutons appearing. We've talked a lot about volcanoes exploding, different types of magmas coming up. Cool. What if the volcano don't explode? That's a pretty good question. If the volcano does not explode, we have what's called a pluton, as shown here. That is, yeah, it's kind of exactly what I said. It's the volcano never erupted, but still had all the magma inside that wanted to erupt. When this happens, we tend to have many different structures form as a result of this lack of eruption of material. Four discussed here are batholiths, stacks, dikes, and sills. These all represent different things that the magma can do instead of popping up to the top of the volcano. The first one is the batholith. These are big magma chambers, essentially. The volcano wanted to grow as a big volcano, but it never popped. All the magma cooled was still inside the material. So these are interesting because, as we've talked about in chapter 3, igneous rocks tend to be very, very hard, very resistant to erosion. So when we get these very exciting, very interesting features, such as the cover of this book, we tend to associate those with things such as batholiths and stacks, because that is the result of essentially volcanic activity that never actually never actually popped up, right? You can imagine all this material here. If this was on top of a volcano, all this material is let loose, shot out of the volcano, you'd have it all on top of the surface, right? If it doesn't shoot out of the volcano, it's stuck in its chamber down here. Over time, sediments get stacked on top, the sediments get taken off, but the batholith itself doesn't get eroded nearly as quickly as, say, the sandstone, this sediment. It's not even sandstone, probably it's just sediment. The sediment here, leaving you with exposed batholith from no material. These things are gigantic. These things are essentially, right? Look at the Coast Range batholith. It's huge, right? Bigger than probably what the size of California, just solid igneous material. And that's because there was a lot of volcanic activity in this part of the world at the point at which this batholith was made, but not all of it was released. Not all of it was able to get out of the volcano. Yeah, here's your Pluton. Dikes and sills, those are essentially different avenues that the volcanic material could take. So that's a really poor picture. I gotta find a better picture of that. Essentially a dike. So remember, you gotta remember, when you have a magma chamber, that is a bunch of liquid, viscous, but still fluid material. It wants to go someplace. It's held under pressure. So if that fluid material happens to find itself and dig itself out a crack between rocks, say in a limestone or something like that, or what have you, it's going to travel into that particular crack. A sill is what happens when that crack happens to be vertical with the bedding. A dike happens when that crack has to be horizontal or perpendicular. I guess I should say parallel and perpendicular. Perpendicular to the bedding, you get a dike. They shoot up like this. Again, picture the amazing geology of the western part of the United States, and the sills are going to be parallel to the bedding. Those are just kind of flat, right? We talked a bit about lavas already. We did chapter 3 in Pyroclast. I'm not going to go too deep into them here, but these are all parts of the volcanic conversation as well. Pahoehoe is your ropey, syrupy lava. Aha is your rubbly, cindery lava. Pahoehoe is what you probably picture when you think of lava flows, and aha tend to be what you get, which is kind of ugly and it runs over and kills everything. Here we have some columnar basalts. These guys are super interesting and super weird to think about, right? You look at that and you're like, okay, that's natural. Give me a break, right? But they are. These columnar basalts, such as the Devil's Postpile in National Monument, California, are the result of unique forms of weathering and unique environments around their deposition and subsequent erosion. If you'd like to know more about these particular subjects, I don't want to go too off topic. If you'd like to know more about columnar basalts and all the other various ridiculous things in geology, again, shoot me a comment. I can dive deeper into this. Or honestly, YouTube it. YouTube the conversation. Find something that looks respectable. SciShow or something like that usually does a good job, and learn a bit more about it, right? It's cool stuff. Within volcanoes, however, we can have different ways they erupt. The different ways they erupt can be fissure eruptions or low viscosity lava extruding from cracks, flood basalts, which are very large, rapid fissure eruptions, and plateaus, which are really big, usually basalts. Right here, we can look at an example of some of these in development here. We are looking at, I don't know, the Snake River in Washington, south of Spokane. This is a canyon. And what we have here is, right, that is a lot of igneous material. How the igneous material get there? Well, that's probably a flood basalt or a slow releasing of lavas over time, stacking up tall and thick, like just layers and layers and layers of lava span out for stupid amounts of time. And then subsequently, the river happens to cut through it and chop it down. Right? Notice here, this green, this is all igneous material, right? These basins, these plateaus, what have you, all old igneous rock, all old lava. Let's see here. What else should we discuss? Yeah, I could probably try to finish this. How many want to chat? How much more I got? No, I might be able to finish this. So that's all cool. Let's talk different types of volcanoes. Hopefully you have a kind of an understanding of how volcanoes work. We tend to classify volcanoes into three distinct categories: shield, cinder, and composite. Shield volcanoes are basically gigantic volcanoes. They are so big that they kind of form a big shield over the earth. Cinder cones are little teeny volcanoes. Short little ones. Sometimes they spit out the sides of other volcanoes. And your composite volcano is when you picture a volcano, you're picturing a composite volcano, like the sharp rise in them and what have you. Stratovolcanoes would be another word for that. Composite volcanoes, stratovolcanoes are your your idealized ones. Here's some tables going over some information on what we mean by these different volcano types. Yeah, kind of a repeat of what I just said. I will point out here those size differences. Million square kilometers in area, 1-2 kilometers thick. When I say shield volcanoes are big, Salt Plateau shield volcano, I mean they're big. Yeah. Then we have smaller shield volcanoes such as Hawaii here, and then five cinder cones are just little teeny tiny things. Composite volcanoes, that's your classic Mount Vesuvius, Mount St. Helens, what have you. Then we can get to calderas, which are caved-in volcanoes. And this all works a heck of a lot better if I show you images. Like if you're me, I have images to show you, right? Here we have some hot gases rising from vents in the crater of the Maroon volcano on the island nation of Vanuatu. I'm sorry about the mispronunciation. Why do we call this a crater volcano? Well, because it's a crater. That's kind of the extent of it, right? This volcano used to probably be a classic stratovolcano, classic composite volcano, where it was very tall like that. But it collapsed in on itself while still being active. So the original volcano is now collapsed in this crater while still venting off the energy and the tectonics. Here's a shield volcano. It's pretty big, right? That's kind of how we classify it. This is huge, big old, very slow, very lumbering giant of a volcano. Typical low angle slopes as shown here. These two could have the same amount of tectonic activity. It's very possible. But I can definitely tell there's a big size difference here, right? Here are some cinder volcanoes visible in the foreground right here. These are very short-lived, very excited volcanic builds, essentially. The magma is pushing the soil up, creating these small, in comparison to this shield back here, these small volcanic, volcanoes. I don't know, I'm trying to say a different way. Yeah, small volcanoes. And of course, your composites, your stratovolcanoes, such as Mount Hood back here. They're called composites because of the different layers of pyroclastic debris that built it. And yeah, when I say stratovolcano, composite volcano, what you're picturing is classic volcano. Pyroclastic flows, we talked about that in chapter 3, right? Pyroclastic flows are essentially when the volcano spits up, if it's not lava, it's pyroclastic material, airborne ashes, airborne gases, shooting out volcanic bombs, all that scary stuff from the movies. There you go. Talked about calderas already, so I can go too deep into that. Yeah, as I said, you got a structure forming, a volcano building up. It happens to release the energy in such a way that it collapses on top of itself, creating a caldera. I don't think I need to go too deep into that. Pyroclastic flow, right? This is, again, pyroclastic flows are all the stuff out of the volcano that's not just the lava, in simple terms. Those big gases, all the explosions. There's probably lots of rocks flying out of this stuff as well. This is dangerous material. You don't want to be caught in a pyroclastic flow, believe me. I've never been in one, but just take my word for it. And this stuff settles, and sometimes it can solidify if it's not eroded away, giving us ash flow tuff. Tuff is a rock that is essentially the solidified pyroclastic flow. Look at how airy it is, very light usually, and it's the remains of this. That's kind of cool. Distribution of ash flow tuffs around North America. Again, coincide with volcanic activity. No surprise there. This is a very volcanically heavy zone, very tectonically active zone. This stuff all comes together, right? And then over here, we have calderas that formed between 36 31 million years ago in the Central Basin and Range province of the Sierra Nevadas and Nevada. Yeah, this is all tectonic activity, but each volcano is going to have its own story to tell. Why is this particular location a caldera? Well, the magma happened to show up in a place that had fractures and cracking, and it cracked in a certain way that instead of pushing up through to make a nice big stratovolcano or pushing up a lot of little tiny spots to make a bunch of cinder volcanoes, as shown here, right below these cinder volcanoes, looks like this. But this magma happened to pop up through these cracks and form little volcanoes, where in this example, it collapsed in on itself. Let's continue this conversation. Yellowstone is basically a gigantic caldera, gigantic volcano. It's commonly talked about in sci-pop sort of avenues that Yellowstone could erupt at any minute and basically kill all life in North America. It's technically true, but not too worried about it. I don't live my day-to-day life assuming Yellowstone's going to erupt, because if it did, not like much I can do about it, right? Very large, though, as shown here. Yosemite's Long Valley, the Bishop Tuff, is 170 times larger than Mount St. Helens and is still active magmatically. So, regional predictions. What do we do about volcanoes? How can we treat them in a risk assessment manner? Well, volcanoes tend to exist where you know they exist. Subduction zones, spraying centers, hotspots, what have you. And volcanic violence of the volcanic activity is related to the type of rock you have and the type of area where they're found. Continental granitic rock tends to be more violent given its silica and water contents, and basaltic rock tends to be less violent, again, given its viscosity and what have you. In a short-term solution, just watch the volcano. If it looks like it's going to stop popping, let people know to get out of the way. There's many different ways to assess this. You can look at gas emissions, track its temperature, earthquakes, right? Earthquakes play a big factor in this because it's magma moving, buckling the soil below it. A couple of big volcanoes, Mount St. Helens, happen. There's lots of earthquakes, swarms of gas and ash. So much so that the United States Geologic Survey, or the USGS, predicted Mount St. Helens would erupt and got a lot of the people that could have been negatively affected by it out of the way, averting large losses. Or you have the Montserrat volcano in 1997. Again, you can look at the history of that volcano. We have earthquake swarms 92. We have steam and ash producing in 95. Volcano's going to go soon. 97 it hits. We're able to get people out of there effectively and reduce fatalities down to 19. We know we have a good understanding of what volcanoes do before they do it, meaning we are able to somewhat accurately predict where they're going to blow. Can I tell you to the day, to the hour? No. But I can say the next couple of years, this is something we need to watch, right? If we look at these numbers for these old volcanoes before we really understood how this stuff works, we can see lots of people dying, right? 10,000, 12,000, 80,000 people dying as a result of these volcanic eruptions. And then as it goes, as we get further along in the process, we find these numbers steadily dropping, with the exception of the Columbia volcano in 1985. But then this also goes into my conversation about earthquakes, wherein you do have a conversation of the more wealthy the country is, the easier it is to track volcanoes and see what happens. Modern volcanoes, you really you tend not to have the destructive results from modern volcanic eruptions, because most every volcano on the earth is being actively monitored for events such like this to avoid loss of life, loss of property, what have you. Pinatubo volcano in 91, right? Large volcanic eruption. The weird part about the volcanoes is that's a lot of energy, a lot of heat, a lot of ash, a lot of stuff goes down with volcanoes. I talk about a lot how Mount St. Helens blew and we had dust from Mount St. Helens over landing in like Minnesota. That's a long way to travel for that stuff. And Mount St. Helens was kind of small in terms of volcanoes. So 1991, we have volcanic eruption that caused a change in the global climate just by that one volcano erupting. And keep in mind, Mount St. Helens, Pinatubo, what have you, small volcanoes, we have evidence of large igneous deposits, large plutonic deposits, meaning lots of active volcanoes going off all at once. It is thought that the Permian extinction happened about 248 million years ago. That is the result of massive volcanic eruptions happening, the Siberian flood basalts, gigantic amount of igneous material existing, massive amounts of volcanism happening, essentially killing off most all life on Earth. Super ridiculous, right? You can link volcanoes with effects on climate. As shown here, the impact of explosive volcanic eruptions on the main climate variability models, showing that you have something go down, a volcano happens, it's going to affect the global temperature. Look at this. Look how high this temperature spiked here for Pinatubo. Look at how much the climate model had to adjust to the volcanic eruption, right? Massive. That being said, of course, this is not a refutation of man-made climate change. It's just adding to the problem. If you already have man-made climate change and a volcano erupts, you're exacerbating the damage. Cool. That was volcanoes. We were able to get through the entirety of the chapter. If you have any comments or questions, let me know down below. This one's a bit tough to get through. Volcanoes are a very exciting and interesting conversation to have. I suggest, of course, look into this stuff further if it's of interest to you. I know who doesn't like volcanoes, right? They're awesome. But yeah, look into this stuff further. Comment down below any questions you have. Hit me up on Canvas or Moodle, whatever program I'm using this year. And yeah, thanks for watching. Take care and have a good day out there.